In this presentation, I'm going to talk about how to go about pen testing multi-tenant Kubernetes clusters. I originally gave this presentation at a couple OWASP conferences, and they did not release those videos. So I'm re-recording it so that other people can check out the tool that VirtueKube made and hear about this topic more. So first, I want to ask you kind of a big picture question to consider throughout this presentation. What level of isolation and security does your Kubernetes cluster provide, and how do you know that? Do role-based authorization controls successfully isolate resources across your namespaces? Can teams deploy dangerous pod configurations that might lead to the compromise of a worker node? Can a malicious developer hijack another team's ingress route, DNS entry, TLS certificate, or secret? Did you know that inside of a Kubernetes cluster, network traffic is completely unrestricted between pods? Unlike Docker Swarm, where you have to explicitly allow traffic between workloads. Finally, in a cloud environment, depending on the environment, network traffic is also completely unrestricted between the pods and the VPC they exist in. So if you have other workloads in the same VPC, the pods can talk to them and they can talk to your pods without having to go through ingress. What would happen if you had a pod that was vulnerable to remote code execution and it was compromised? What if a developer accidentally deployed a pod containing malware, or a developer's credentials were compromised? What other networks are connected to your VPC in the cloud, such as an internal network, that a compromised pod could reach out to and actually reach inside your internal network from the cloud? So considering some of these threats, a lot of people use audit-based tools to assess their Kubernetes cluster. And I want you to ask yourself, do you think these rule-based auditing tools are going to be effective at identifying these risks? And how much confidence would you have in the results if they told you everything's great, your pod or your cluster is secure? So bringing it back to the big picture question, how do you know what level of isolation and security you've achieved in your Kubernetes cluster? That's what we're going to talk about today. We're going to get hands-on and attack a real cluster and its workloads. We're also going to introduce a new tool I've written. We are going to focus a lot on demos. Before we get to demos, I need to do a little bit of background on Kubernetes. I'm not going to go in depth about that background. We're going to skip a lot of things that people might think are important. I'm going to touch on just the most important things that I need as background for what I'm going to explain later in the demos. We're also going to talk about a typical journey an organization might go through when they have lots of Kubernetes clusters and they might choose to transition to a very small number of multi-tenant clusters. So a little bit about me. I work for VirtueKube as a penetration tester. I do application pen testing, cloud pen testing, and Kubernetes pen testing. On the application side, I work with everything from single-page applications and REST APIs to desktop applications and Android mobile applications as well. So let's go and get started. Briefly, what is Kubernetes? We're going to pretend that you are a software developer and you write microservices, middleware, and single-page applications. And there are dependencies you need for those components to function. Your team has discovered how wonderful it is to bundle your application and its dependencies together into a container that you can then bring to any server and it just runs. It's very convenient. It works every single time. However, because of your success, you now need to be able to reliably deploy multiple containers that all depend upon one another, use automation, scale out those deployments based on load, and a variety of other sophisticated tasks. That's where Kubernetes comes in. Kubernetes is an open source system for automating the deployment, scaling, and management of containerized applications. It provides a rich ecosystem, not just for the containers, but additional supporting infrastructure and plumbing to make life easier. So a couple concepts around Kubernetes that's important that we talk about. In Kubernetes, our smallest unit of work that we talk about is called a pod. Pods have one or more containers inside of them. Pod is usually part of a larger definition of Kubernetes specs like a deployment and service, ingress, and things like that. Those deployments then tell Kubernetes how you'd like those pods replicated and distributed across multiple servers for high availability. It also tells Kubernetes how to reach the different services running on the pods from inside the cluster, how to route traffic to pods from outside of the cluster, how to magically get secrets injected into the pods, how to use TLS certificates for ingress, and just a whole lot more. Kubernetes is popular because it's portable across commercial, cloud, and open source cluster implementations. You can host in the cloud, you can host in your data center, it runs on a Raspberry Pi, it can work on a developer's laptop, It can go just about anywhere with very little changes as a result of moving it from one place to another. In other words, virtually no vendor lock-in. With it, you get scalability, high availability, self-healing, and a lot more benefits listed on this slide. So rightfully so, there's a lot of excitement from teams using Kubernetes. So naturally, why don't we go ahead and Kubernetes everything at our organization? Maybe every single team needs their own Kubernetes cluster. And really, they probably need 3 because they need one for dev, one for staging, and one for production. We really want the teams to have a lot of freedom and be able to choose which Kubernetes implementation they want. So we're going to let them decide if they want open source or cloud or commercial. So when we do that, this is what happens. We end up with a whole bunch of clusters using a whole bunch of different products. We don't necessarily have anyone in particular in charge of any of them. We may have clusters that were set up by employees that no longer work there, clusters that everybody just hopes and prays still works because they don't know how to update it and manage it. We really don't patch anything because that might break it, and we're scared to touch them. We didn't really get that high availability, that self-healing, that all those benefits because now we have this fragile system that nobody's really in charge of, and we're not sure what's going to happen if we touch it. We also forgot that inside this cluster, there's a whole bunch of sort of plugins and shared services that run that are used to make our life easier. But again, we don't really understand what they are, how they work, because the person that set it up doesn't work here anymore. We don't patch these things. We may just stop using them. They just sit around. We're not sure how to make them work. The solution of just having every development team kind of do their own thing, manage their own cluster, it might work for some teams, but for most, it's not going to be a very successful strategy. Let's try again. How about if instead we create a platform team? It's a specialized group of individuals who are going to take on all the tasks of creating clusters, upgrading and patching clusters, managing them, making sure they work, just taking care of them. We can have them troubleshoot anything that goes wrong during deployment with the development team. They can stay up late for those deployments, but we also want them to do a bunch of cool things like implement GitOps. If we go back to this slide with all these disparate Kubernetes products and versions, having a small team try to do the same thing the developers are trying to do, it might be slightly more successful, but it's still not going to work because you have a small team managing a whole bunch of clusters, trying to make them all work, all function. They're never going to get around to patching them all or adding new features and making them these wonderful platforms that developers love to use. They're going to always be playing catch up. It's not going to work. So again, let's reimagine what we might do. What if instead of having tons and tons of clusters for each team and product, what if we had a really small number, 1 or 2 or 3? The platform team, we still had a platform team, but maybe they managed just the 1 or 2 or 3 clusters. And they can make it amazing. What if it was just a joy to use and it was always up to date? And dev, staging, and production had almost the same stuff in it, almost the same versions. It was reliable. What would that look like? Well, it might start out looking something like this. This is one way to do a multi-tenant cluster, and this is kind of doing it yourself and doing it manually. But we have some really important concepts here that's going to allow this to happen. First, we have a bunch of different development teams. They don't necessarily have the authorization to go and mess with other teams' workloads or code or containers. We need some kind of isolation. We need it so that one team cannot mess with another team's workloads. We do that by using namespaces. Namespaces are like folders that files fit in, but instead these folders hold pods and other Kubernetes specs. And by themselves, namespaces don't really do a whole lot. But once these things are in namespaces, we can start applying authorization controls. And we could say Team 2 can get to everything in Team 2's namespace and nothing in any other namespace, including the platform team's shared services or Team 1's workloads. So we start having isolation. We also want resource limits, and there's a couple ways to do this, isolating teams' workloads onto different nodes, but let's pretend that we're not doing that. Let's say we're sharing nodes. We want to make sure that none of the teams can use up all the CPU and all the RAM available on a particular node, starving another team's workloads of resources. So we need some kind of limits along those lines. I'm not going to talk about that part in this presentation too much. I'm more interested in the authorization controls. This setup is actually pretty decent. This is a really good start, especially for a real small organization that has, 1 or 2 teams maybe. But as we get bigger and we have more teams, this is going to be a little bit harder to manage. we're going to start having situations where as we get to 10, 20, 30 development teams, there's going to be things that the developers would like to do and can't because the platform team can't give them authorization to, for example, create arbitrary ingress rules. Because when you do that, you can actually hijack traffic from other teams' namespaces because of just the way it works. So there's certain resources that aren't safe to allow developers to create directly. We're going to need to have the platform team do that. The platform team is going to eventually become a bottleneck for that. And we need some way to speed that up and have more self-service with controls around it. What we might like to do is start looking at plugins. Kubernetes, it has a plugin framework that lets you add custom resources and admission controllers and a lot of other things to provide additional functionality in the cluster. And so while Kubernetes may not have a native idea of a tenant, you could use something like Capsule, which does define tenancy and applies additional rules and access controls around what users can do and helping them to do it safely, giving them the ability to create ingress, for example, or other things that might not normally be safe. In addition, we need a policy enforcement plugin like Kubernetes that can do some other really important things. And to explain that, I actually need to back up a little bit about some of the technology behind these containers in Kubernetes. So pods run containers. Containers are essentially processes that run on some kind of worker node, some kind of server, and they're sort of isolated so that they can't break out and see and talk to other processes running on that server. There's some features in the Linux kernel used to do that, but in general, one of the things that is a limitation is if you allow a pod or a container to have root access inside of its own process, what you're really doing is you're giving it root access to the underlying node, the underlying server. In some cases, attackers may not be able to use that to break out and harm the node, but in a lot of cases, once you start allowing root processes to run inside of a container, you have this real risk that they could compromise the worker node, the server, and then from there they could compromise all the workloads running on that node and sometimes the rest of the cluster. So we can't let developers run containers as root. There's a lot of other things we can't allow anyone to do safely, and so Kubernetes has a way to define these policies that as you add a pod to a cluster, it can reject them and say, hey, I know you're authorized to create a pod, but this pod violates our policies, and I'm gonna have to say no. You can't deploy this pod in this cluster. With those things together, we have a much better system in which we can allow developers to self-service and create some of those riskier Kubernetes resources. Let's pretend that we have this super cool cluster. It's multi-tenant. We're feeling pretty good about role-based access controls. We got policy enforcement. We got tenancy. We have a lot of other things in here that we think are going really well. And we want to know, do we do it? Do we isolate our tenants well enough? Is it safe and secure? How do we find out? Well, the answer is not to run an auditing tool. The auditing tool is not going to understand most custom resources. It's not going to be able to tell you for sure permitted and what's not, because some of the admission controllers are going to be enforcing that, not role-based access controls. What you really have to do is you have to go in and attempt to do something you're not allowed to and observe whether you end up being allowed to or not. So that's where pen testing comes in. We want to basically exercise the different test cases in the Kubernetes cluster to find out if we have achieved the correct level of isolation. How can we do that? Well, we're going to simulate some common scenarios that attackers might have the opportunity to perform attacks in. We're going to look at a pod with remote code execution vulnerability that gets compromised. We're going to look at a container that someone accidentally typed in the wrong name and instead deployed malware. We're going to look at a compromised developer account and what that person could do if they're in a separate kind of tenant. Could they reach into other tenants and cause harm? So we're going to look at all those situations, and luckily, these are things that can be looked at all at once if you approach it from the right perspective. If we approach this as a compromised developer account, we can actually exercise the compromised pod, the pod or the container with malware, compromised developer account in a different tenant or namespace, or malicious developer. We can actually go through and exercise all of those, and as we do that, attribute it to the right situation. So to do that, we need to, one, create a developer account that's going to simulate that compromised developer. And then we actually need a read-only access Kubernetes service account or user that can see everything in the cluster. And this is going to be critical because We don't want to guess what resources are in there or what we need to try to get to. We want to actually try to get to all of them and for the cluster to tell us no. That's how we know if we have the correct level of isolation. The only way to do that is if we have read-only access to see everything and then attempt it. Let's talk about our cluster first and what we will see in our cluster. So right now I have a K3s cluster with Capsule and Kubernetes running with some simulated developer workloads. What we're going to do first is we're going to look at the tenants in this cluster. And we have 3 tenants, a team A, a team B, and team C. We're going to go ahead and say that team A and team C are real actual development accounts or workspaces or tenants with real workloads. And we're going to say that team B is actually going to be the simulated compromised developer account. It's kind of like the bad guy. In these tenants, let's take a look at how they're defined. The first tenant is team A here. Team A has a namespace currently called team A test. So Kubernetes namespace called team A test. In team A test, we have a owner. It's going to be Alice SA, so Alice service account in this case. And Alice is going to be granted the following cluster roles: admin, capsule namespace deleter, and capsule tenant ingress route creator. While these cluster roles sound like they would apply to all namespaces, it's actually only going to apply to her namespaces, her tenant. Basically, this is giving her admin access to the team A test and any other namespaces she creates for her tenant. Now, if we go down to look at team B, we need to simulate again the same kind of account, the same kind of tenant, but we want it actually to be on a different tenant to see what one tenant could do to another. And so our attacker tenant is going to be team B. Team B has the same exact permissions. So we're going to be Bob service account. And again, we have admin, namespace deleter, and ingress route creator. And we have one namespace of our own called team B test. We're going to use this to attack team A and team C. Now, if we actually look in the namespaces for team A test, we're going to see all the workloads that Alice has running in her Kubernetes cluster. These are examples of some of the targets that we're going to go after. Similarly, we can look at team B. This is what our attacker has currently running. And then if we actually get all the namespaces, I want to show that there's a whole lot here more than just the tenants. So we're going to see namespaces for Capsule, Cert Manager, the Kube system, Kubernetes, monitoring, platform team. These are all namespaces that belong to the platform team or the Kubernetes cluster administrators. It's not something that either the attacker or team A or team C should be able to get to. These are kind of off limits. All right, we want to be able to, as the team B test person, so Bob, the attacker, we want to try to get at all these resources. To do that, we're going to need to be able to see everything that's in the cluster. Currently, we're running as a read-only user. I can kind of show you that. So if you look at our context, we're using this read-only service account context. What we need to do is, to start with, is get a list of everything that's in the cluster. If we were to do that normally, we might do something like kube control get all minus all namespaces, so minus A. And it would list what we would expect to be all things, all resources in the cluster. However, this is not really true. The get all command is actually kind of like an alias, and it only has a subset of things in the cluster. And we can demonstrate that if we were to just do things like count the number of lines in the get all command, we get 137 things. If we were to instead use this command to truly count everything in here, we would get closer to 1,000 things. All right, so we got 3,930 things as opposed to the 137 things. So we have to ask ourselves, do we want to manually create a way to try to gain access to 3,930 things? Or do we want to try to automate this somehow? And this is the problem that I had faced in the past about the sheer scale of some of these clusters, the inability to do this systematically and repeatedly. I needed a way to execute these different test cases, assessment after assessment, kind of do it in the same exact manner and kind of cover everything. I decided to make a pen testing tool called VirtueKube. And VirtueKube is going to do a couple things like get a list of all resources and export them, and then execute test cases for things like authorization vulnerabilities or trying to get secrets or a whole lot more. So if I do use the help command, we're going to see a list of subcommands that are available. Dump cluster is the one you always start with. It's going to create a list of resources that the rest of the commands are going to use to scaffold test cases and look at the cluster for different vulnerabilities. So let's go ahead and run this command, and we're going to go and get everything that's in the cluster. So it's going to go through that read-only account. It's going to go through and get everything in here, and it's going to output a JSON and a YAML representation of each type of thing, each namespace, and then 2 centralized files for all that JSON and all that YAML. It's also going to help us visualize what's been installed via Helm. It's going to create a CSV export of all of this, and it's going to create a markdown file. So a couple different options for how we want to view this information. Let's go ahead and pull up some of this and look to see what that might look like. First, if I come over here and look at the output folder, we're going to see that there's an all.json and an all.yaml. These files contain the same list of resources, just in the 2 different formats, JSON versus YAML. So whatever your preference is, you can kind of use it. The tool actually relies on the JSON version. That's how it knows whether a resource exists and to be able to craft a test case for it. If we were to, let's go ahead and look at an example of one of these. Let's do the YAML version. If we were to look at it, it would look just like the output from the kube control command. We could go through and see what's in the cluster, kind of see it as we would normally expect to see it. Okay, so we also created, a lot of these others are things we'll create later, but we created these 3 folders. And in these 3 folders, we have the YAML and JSON representation of each type of resource, regardless of namespace. In the namespace folder, we have, for all namespaces, each type of item. And then in the all folder, we have a CSV and a markdown representation of what's in the cluster. Let's go and open the CSV version of this. And what you'll see here is an output that's real similar to a lot of cloud pen testing tools. We're going to see which specific namespace a particular resource is found in, kind of like which region a resource might be found in for an AWS pen test. And then you see the type of resource on the left, and then a count in the middle. So we can see things like in the non-namespaced section of the Kubernetes cluster, there's 114 cluster roles. Or we could look at the kube system has 14 add-ons, or let's find pods. We look at pods, we can see there's 2 in this namespace, 3 in this namespace, 7 in that namespace. This is going to help us kind of visualize what's in the cluster, where the most interesting resources are to maybe go after manually later. We're going to be able to go after all these first through automated test cases, but later we're going to be interested in looking at this from a manual pen testing perspective after we use this tool. Okay, one of the other goals for the output from this tool is to be able to use other tools that's on your system to look for things that you're interested in for the Kubernetes cluster. So I have one example of just simply using JQ to search for example, pods that are not in the kube system namespace, and then print out the name of the pod and which namespace it's in. And we're going to use the all.json for that. This is just a demonstration that we can use JQ, and we'll be able to use lots of other tools on these resources without having to make another round trip to the cluster. We can also do things like run git leaks. So because I have a listing of all the Kubernetes specs in the cluster, I'm going to choose by resource instead of by namespace. What I can do is I can have git leaks go through and look for any embedded secrets in those files and then be able to quickly evaluate them. So it says it found 43. Let's go take a look at that. We can go through and look at what secrets were revealed. We can do it by resource type because we looked at the by resource folder. What we're going to find is there are some interesting secrets in here. Like this one is an admin password that's hard-coded into, oh, this is a secrets file. Let's find something that's not a secrets file. It's still a secrets file. Here's a deployment. All right, so here's a deployment with some kind of secret embedded in the deployment file. not a reference to a Kubernetes secret, but someone hard-coded a secret into the deployment for that resource. That's something you don't want to do, but we have to ask ourselves some really important questions in a pen test. Depending on what namespace this is in, what the cluster roles are, what the roles are within a namespace, we might have a hard-coded secret that's bad, but nobody may be able to get to it. We don't know what the authorization controls look like. We don't know if we can actually go after it. And so we want to know, can our attackers see this? Well, how do we find that? Well, we could go resource by resource and manually do kube control get and then whatever the resource is, and then kind of look in the YAML and things like that. But when that's a really huge set of resources in the cluster, that gets old really quick. So what we really want to do is we want to automate that. What we should do is go ahead and switch to our attacker perspective now. We have an export of everything in the cluster. Let's try to use our tool to get to some of these things. But first, before I do that, let's go ahead and actually explore a couple things as Bob the attacker, because this also helps demonstrate how difficult this can be sometimes. So first, we're Bob the attacker. We have admin rights to our namespace. We should be able to ask the Kubernetes cluster, hey, give me a list of namespaces that are mine. So if we say, as Bob the attacker, kube control get namespaces, what we actually get is an access denied. And what's happening here is we don't have the permissions to list namespaces. We can't see all the namespaces in the cluster. This would be a problem if we did not have another account with read-only access to see what our targets should be. We would kind of be stuck with guessing what namespaces might exist and trying to get to them, and then guessing pods or other resources in those namespaces. Well, despite the fact that we can't list namespaces, we can list the items in our particular namespace. So if I do a get all on team test as Bob, we can see that I have a bunch of resources defined. If I were to try to get Alice's, kube control get all Alice's, it'll tell me access denied. I do not have permission to get or to list Alice's resources. All right, so let's pretend in this cluster there are some resources that have improper access controls. The cluster roles or the roles in the namespace are defined poorly and they're left open and an attacker can get to them. What might that look like? If we knew the name of the namespace, we might be able to just list it. So in this case, we did a kube control get all -in, so the namespace called unprotected. We can see that there is a pod in there. If we were to dig a little further, we would see, again, the get all isn't really all. If we were to say, hey, list this pods and service accounts, we'd see that there's also a service account in there. But how do we automate that? What I want to do is Bob the attacker with limited ability to see what's in the cluster. I want to try to use the export of what we know is there to go ahead and exercise authorization controls. What I'm going to use is this command called exploit from VirtueKube, and it's going to go through, in this case, and look for secrets and service accounts that have improper authorization controls applied. It's going to do more than that, though. We can obviously try to do kube control get and then a secret and see if it works, but there's other ways of getting secrets. If a pod has mounted a secret, it's going to be available in its file system under varlib, I believe, secrets. I have to actually double check that. Kubernetes.io/secrets. I can't remember for sure. But it's going to be mounted in the pods. So if we don't have access to a secret, but we have access to a pod and we can exec into it, we can still get that secret. That's one of the things this tool is going to do. It's going to exec into pods. It's going to try to copy files using kube control copy from pods. It's also going to go to service account files and it's going to try to get service accounts. It's going to try to create service accounts or create token on service accounts. And it's going to look inside pods for those items. So let's go ahead and try this and see what happens. Again, we're running this as Bob. And it's going to go through and it's going to look at secrets, pods, service accounts, and then let us know what it was able to do. All right, it's complete. It made us a text file, a CSV file, and a markdown file. Let's explore the CSV version and see what happened. Okay, if we were to look at the output, we're going to see first what kind of resource we were going after. We can see which namespace we tried to attack, the name of the resource. So this would be the default resource of type service account in team test. It's going to tell us whether we were successful. It says true. It's going to tell us the technique used to do the attack, and it's going to give us the token it was able to extract. Couple things. We are Bob, and we have access to team B test. Therefore, we do not care about results that are in namespace team B test. We don't want to see those. So I'm going to just say hide. We're not going to look at those. We are interested in the namespace unprotected. We're not really supposed to be able to get in there. And I demonstrated before that we could because of misconfigured access controls. But this did a much better job of exploring that. What this thing is saying is for the service account default in the unprotected namespace, it was able to call kube control create token on that service account. On a pod named nginx unprotected in the unprotected namespace, it was able to call kube control copy and to get a file out of the container and onto our file system that we were able to get. Last, same pod, we were able to call kube control exec and get a shell into the pod and then cat out the service token or the service account token from that pod. So 3 different ways, 3 different kinds of authorization violations for that namespace. This, when done across an entire cluster for all the resources in a fairly complex cluster, is a real time saver. And it's systematic. It's going to have a deterministic result. It's going to work or it's not going to work, and it should be the same results every time. This is a big reason why I wrote this tool, but there's so many more. Let's talk about networking now instead. Actually, no, sorry, there's one more command I want to try. And that is, we have this test resource access kube control command. What this does is it literally looks at everything in the cluster, not just secrets and service accounts, but it looks at every kind of resource in the entire cluster. And it tries to either get or update by annotating it, which should not cause a redeployment, should not, but don't do this in production. And then, or both, it'll try to do both to it. We're going to run the both, and we're going to see a better idea of what we can do to all the different resources in the cluster. While this is running, let's go ahead and look at a previous version of this tool's output that I ran. When I ran this previously, we saw a couple of resources beyond the secrets and service accounts we saw before that we were able to get to. So again, we want to ignore team B test namespace. So we're going to hide that. But what we are interested is anything in another namespace. So we saw in the unprotected namespace, we can modify the config map kube-root-ca cert for that namespace. That's new that we didn't know before. And we can modify the pod called nginx unprotected. There's a couple columns here on the left. It tells you whether the get portion was successful. And then over here, it tells you whether the update portion was successful. So if you notice, we are able to do things like get the unprotected namespace, but we could not update the unprotected namespace. But we're able to update config map, pod, and service account. So again, this applied to everything across the cluster gives you a really good idea of what you can get access to. And that's going to drive manual testing after that. Once you know what you can affect in this way, you can come up with some sort of strategy for escalating privileges by getting service account tokens, which really apply to the other spreadsheet I showed you, or execing to pods, or modifying pods, or deploying work loads in other namespaces and things like that. So that's super helpful. Okay, I'm going to stop this. We're next going to go in to talk about networking. In terms of networking in a Kubernetes cluster, by default, unless you do something, all pods in any namespace can talk to any other pod in any other namespace. There's no network restrictions. Now you can put network restrictions in place if the networking plugin you're using supports it through network policies. And there may be other ways of doing this as well, but network policies is kind of the built-in way to do that. And they kind of act as like ingress and egress firewall rules. You can say who can talk to what in what namespace and things like that. But by default, there are no rules. Everyone can talk to everybody. This means that if we're an attacker in our own namespace, or we're a compromised pod or something like that, it means we can talk to anything we want and check for services running, applications that haven't been patched and have known CVEs. We can, in a cloud environment, reach out to EC2 instances that are in the same VPC, or if there's a transit gateway between the VPC and the internal network, we can start going into the internal network from there. And so one of the tasks in one of these pen tests is to check to see what we can do. What ports are open, what services are available, whether authentication is required, things like that. Before we jump into how to do that, we need to talk about ports in terms of pods and services. So we're going to look for a particular pod in here. So we're going to look in Alice's namespace. In Alice's namespace, we have a pod. The pod's name is Nginx deployment and some characters added on because it was done through a deployment instead of a pod. Inside of this specification, we're going to see a couple of really interesting things. Here we go, containers. We have a container inside of this pod called Nginx. It's running the container image tag with Nginx latest, which is not a best practice. You should use a specific version tag, not latest. But in this case, we're using Nginx latest. And it tells us that it has a port open on port 80. We might look at this and think, hey, this is amazing. If we need to look inside of the Kubernetes cluster for open ports and services and check to see if they require authentication or authorization, or if they're running a out-of-date vulnerable software, we just go here and get a list of all the ports, and it'll be really quick to do. In addition, these pods, not the containers, but the pods have IP addresses. So if we go down to the status section, we're going to see the IP address of the pod. And we can use this to sort of in-map scan the cluster and find out what ports are open and what services they have. Now, something that's really important to point out is these IP addresses are reliable. The ports are not. And I'm going to demonstrate why that is. I want you to remember that this Nginx server is supposed to be listening on port 80. It's Nginx latest, and it's in Alice's namespace. If we go and look at another one, here's a pod in Alice's namespace as well. That's of type pod. If we go and look at its definition, all right, it's called Nginx undeclared port. It is also running Nginx latest. In the other definition right here is where we had that port declaration. It would say, hey, something's running on port 80. Now, my question to you is, since it doesn't list an open port, does that mean we can't get to it? Does that mean that port is closed or that it doesn't exist? Let's kind of find out. In order to do this, I'm going to switch to the read-only context again for a moment. With this read-only context, we're going to use a feature of kube control that lets us port forward from outside the cluster to a very specific pod, whatever we name. And it's going to say, send our current local 8001 port to port 80 on this Nginx undeclared port. If this port is not open, if it doesn't exist, we shouldn't be able to get here. This shouldn't work. Let's find out if it does. So what we can do is we need to go to localhost 127.0.0.1 port 8001 and see if we get the Nginx startup page. So if we do that, we can see, hey, welcome to Nginx. It worked. What this is demonstrating is port declarations inside the cluster do not have any bearing on whether or not a port actually really exists, or whether there's firewall rules or some kind of protection stopping you from getting to it. Those ports you basically have to ignore. It also means that if you're going to scan the cluster for open ports, you have to do all ports, 1 to 65535, to see if the ports are really open. There's no way to really tell otherwise if it has an open port. There's hints through services, there's hints through the pod specs, but they may not be accurate. They may leave things out. There may be a lot more open than you think. Another thing to demonstrate is we did this as the read-only user that can see everything in the cluster. If we switch back to Bob and we try to run the same command to forward our local port to port 80 inside of Alice's namespace, teammate test, you're going to see that we get an access denied. So an attacker from the outside can't port forward. This is something that we need to overcome in order to test connectivity from the attacker's perspective. Before we do that, though, we need to get a list of targets to go after. And that's another thing that our tool is going to do for us. We're going to run VirtueKube's IP command, and it's going to export a list of all the IPs in the cluster based on the all.json file. So over here we have ingress routes and DNS and IPs and services and ports. There's actually a lot here that you can go and look at. I'm going to show you, let's look at some of these real quick. They're kind of interesting. If we look at service DNS, here's all the DNS names for any Kubernetes services defined. If we look at ingress, you're going to see ingress routes that are defined in the cluster, which this is not the easiest to obtain normally. It's actually a really nice thing to have. What we're going to focus though on is pods. So if we were to cat out the list of pods, we would get a list of all the internal IP addresses in the cluster that belong to the pods. This is what we want to scan. We probably want to scan the nodes as well and look at the ingress, but for now, let's pretend that all we want is the pods. We want to check to see if there's any open ports in these pods. We just demonstrated how we can't port forward to these individual pods, and even if we did, we'd have to do it one port at a time. So one local port to one remote port at a time, and that would not be very fun. What we're going to do is we're actually going to deploy a pod inside of the attacker's namespace, Bob's or Team B Test's namespace, to run Nmap and scan all of these pods for open ports. And then we're going to, when it's done, we're going to download the XML version and the standard output version of the Nmap file locally so that we can have that. So how do we do that? We're going to use this command, Nmap scan, tell it which namespace to deploy the pod into, tell it what we want to scan. We want to scan pods. When we run this, it's going to go through and it's going to start a job, and it's going to iterate through all those IP addresses we just saw, scan ports 0 to 65535. It's going to do service detection. It's going to do, I'd have to look at the code to remember all the things it does, but it's going to go through and try to detect what's there. While this is running, let's go to a previous example of what it found. Okay, so previously, so this CSV has which namespace. Actually, let's come back to this. Let's focus on the IP addresses for now. We said that there's a pod IPs text file that has a list of all the pods. What the Nmap scan did is it did the reverse DNS lookup, which is typical of Nmap. It listed the open ports. It did some service detection to try to tell us what type of protocol it thought it was using. So a lot of these are HTTP. Some are unknown. It thinks this is Jet Direct, which is not correct. Things like that. And then if there's a banner to grab, it goes and grabs the banner, and then it'll also tell you if it's using TLS or not. These are the standard things that any Nmap scan will do with service detection turned on. This command has done on top of that Nmap can't do alone is it's correlated the IP address to a specific resource in the cluster. And what this is saying is there's this IP address 1042.093 belongs to a pod. That pod is named capsule proxy, and it is running in the capsule namespace. So think of this as kind of like a Kubernetes, Nmap variation, except for it's using actual Nmap, and we're just doing the analysis to generate the CSV instead of like creating a new product or something like that. So with this, you're going to get a list of open ports. These open ports now, you're going to want to do something like go witness to go through and screenshot each of the endpoints, or you might want to visit their web pages directly through a proxy. See if there's any services that don't require authentication or showing you something they shouldn't. We're also interested in any outdated software that's running on these. We need a way to use our existing tool set on our computer to run Go Witness, to run other security tools on these inside of the cluster. But we can't port forward as the bad guys, Team B Test. So how are we going to do that? What we're going to do is we're going to use another feature of the tool. I'm going to actually stop this. We're going to use a SOX proxy. So what this command is going to do is it's going to deploy a SOX proxy in our namespace, which we can port forward to. And that SOX proxy is going to allow us to talk to anything in the cluster through the proxy. So right now it's working on deploying a pod. And once it deploys the pod, it's going to give us instructions for setting this up. So on our local host 1080, we have kube control port forwarding to the remote port 1080 on this SOX5 proxy pod. If we were to do something like go to Firefox and say, hey, we'd like a proxy, and it is a SOX proxy, so this one, localhost 1080, and hit OK. We're going to send DNS through it as well. If we wanted to then talk to one of these resources, we could. Let's actually switch to this screen. And what I'm going to do is I'm going to look for the current traffic dashboard endpoint that's in the cluster, which is something that's in the Kube system namespace that we can't normally get to. Alice can't even get to this normally because it's not intentionally being exposed by the platform team. We're going to try to get to it through our proxy. So to get to that dashboard through the SOC 5 proxy, here's that demonstration. We're able to get to that even though it's in the platform team's namespace. We can get a list of all the ingress routes that are defined for all tenants. No authentication was required to get here. There's an assumption that because it was in the Kube system namespace that nobody could reach it, and therefore it didn't necessarily need authorization controls. But that assumes that pods inside the cluster can't talk to other pods without permission. Lots of other services may run unsecured in the cluster, and so you would kind of continue exploring this with other tools that support SOC 5 proxying. Anything that has that proxy support, you can use from your own computer and not have to deploy a pod and shell into it or something like that to run those tools, which is a big help, especially when container images are restricted through a registry or something like that, and you couldn't otherwise do it. All right, so there's a lot more that this tool can do beyond what I've shown. So much more. So this is worth looking into in more detail on your own. We have an example cluster that you can use this against, that you can run in your box. Most of the things I showed in this presentation are set up already in that GitHub repository, Kubernetes Cluster Lab, with exception to the unprotected namespace. That part's not in there. So you can go and practice this yourself. You can go to the github.com/virtuesecurity/VirtueKube to get a copy of this tool and build it using Gradle, and it'll just work. And then feel free to contact me on LinkedIn with feedback about the tools or leave an issue in the VirtueKube repository. Thanks.